So here we're given the original graph, which is the red one, and then they're telling us that there's been some vertical and horizontal compressions, and that resulted in the blue graph. We have to figure out what happened. Now, when we had these questions in the first section, when we were moving things left, right, up, and down, it was really easy to see what happened. But when we get to these questions where we're stretching it and compressing it, it's not as easy just to look at the graph and say, oh, I can see that the y has been multiplied by a half, or I can see that the x has been multiplied by 3. So what we're going to do for this is we're going to set up a system to help us see what's happened. We're going to start, since we always look at the y values first, we're going to start by looking at we're going to pick 2 points on the regular graph, and we're going to pick 2 points on the image graph, and we're going to look at the vertical distances between them. So first of all, on our original graph, we're going to label 2 points. I'm going to call this one down here A, and this one up here B. And so after the transformation, this point A went there, so we're going to mark it with an A prime. And this point B, it changed to be right here. So we're going to mark that with a B prime. So when we're looking at our vertical distances, first we're going to look at how far is it from A to B. We go at -8 all the way up to 9. Looks like it's 17 units in between A and B. And if we would look at the image graph from A prime to B prime, how many units apart are those? It starts at -4. It goes up to 4.5. So the distance is now 8.5. What would you have to do to y values to change a distance from 17 to a distance of 8.5? And for all of our stretches, we always talk about multiplying, right? So what has happened to the distance? Y has been multiplied by a half. We do the same thing with our horizontal distances. If we look from A to B, we go from 2 to 3. That distance is 1. And A prime to B prime, well, that goes from, 1 to 1.5. That distance is a half. So what has x been multiplied by? It's been multiplied by 1/2 as well. So now we know what's happened. We should be able to write the equation of that blue graph in terms of f. How do we show in function notation having y get multiplied by half and having x get multiplied by half? Well, for the y multiplied by half, that happens outside of the function, and so that would appear just in front, 1/2. For the x multiplying by 1/2, that would be something that happens inside the function. And you'd have to do the reciprocal. So it's a half, so inside the function, there would be a 2x. So this one is probably the most complicated question we've looked at so far, in that You've got two graphs, and we have to come up with this strategy of looking at corresponding points and how far was it originally from 2 points, A to B, and how far is it now? Same thing with the horizontal distances. And then once we find out what has happened to the x and y coordinates, then we can go and write out the equation. Later on, you'll get ones where the x and y have been multiplied by something and there's been translations involved. So those will be even more complicated to try and figure out the equation. Questions for this one are 5, 12, 13, and 14. Before we go to those, I'm going to add one more example. And if you turn to page 192, I think there's like a blank page that says extra workspace, so that we can add this example there. Almost all of the questions that we've done in our notes or you've done in the textbook often give you the first graph and ask you to do the transformation. Another type of question that you can see on an exam or on a test is one of those parent graphs that we did on those colored sheets to begin with, just with the equation. So for example, if I got you to graph y equals (3 times -1/2 x cubed), and no graph was given for you for the starting graph. So when your graph is given to you as a starting graph, you can easily pull off a couple points and say, this is what I need to do. When the graph isn't given to you, you have to be able to recognize what is the parent graph, be able to draw a quick sketch of that so that you know what points you're looking at, and then you can do the same thing that we've been doing so far. So, for this one, what's the parent graph? It's just our regular x cubed graph. What does that graph look like? Draw a quick sketch of it here. What are key points on there? 0, 0, 1, 1. -1, -1. So if you know what the parent graph looks like and you can quickly plot some points on there, you can now say, well, where are these points going to go? So I'm going to list my original points on my blue graph. And what's going to happen to them? Well, now let's look for what are the numbers that are different in our equation from our original one. There's a 3 here. It's left to right. That's where we run into first. What is that going to affect? X or y? Y. And we're going to multiply our y by 3. The next thing we run into is the 1 over -2. That's inside the cube, so it's going to affect the x. And things that affect the x are going to be reciprocal, so we're going to multiply by -2, because if you flip that fraction, it's -2 over 1. And now we can see where do those points end up. Y by 3. Oh, thank you. And that'll make this 3 -3. And then the x by -2. And we get 4 new points. Now when we go to graph this, 2, negative 3, 0, 0. Oops, 2, negative 3 is down. 2, negative 3 would be right here, sorry. X by negative 2, this would be negative. Negative 2, 3 would be here. 4 comma, wow, I missed all my negatives, didn't I? Negative 4, 24 would be up here. And so we can get the graph in the end by just looking at our points. Now, I did something that almost all of you are going to do at some time, which is make a simple mistake. I was multiplying by negative 2, and I forgot a couple of negative 2's here. I labeled my point correctly, negative 1 here, but when I wrote it down here, I forgot the negative on one of those. Do you ever make mistakes like that? Or maybe I'm the only one. No, we all make mistakes like that, right? Also because we're trying to do things as fast as possible, graphing these questions on our radar from the most exciting things that we do in the day to the least exciting things that we do in the day. I know that graphing these are usually not right at the top, right? This isn't something like you go home and you just can't wait to tell mom and dad, we graphed today and it was so exciting and I want to show you 10 examples of what I graphed today. So because it's not one of those high priority things for us, our brain does that. It forgets negatives. It sort of glosses over things. And the results of that can be catastrophic because you get doesn't look anything and then you don't know what you did and then you get frustrated and you just quit. So a couple of things that you can have as sort of a setup to check that you're not making those mistakes. And I have the advantage that I've probably graphed thousands of these. So when I make the mistakes, I've got things built in to check as I go along. So they don't end up harming me. Because when I started graphing, I was like, oh, things don't feel right. So I quickly checked my answers. But you haven't done that many questions yet that you have that built-in ability to say this doesn't feel right. In fact, it might all feel wrong for a long time, even when you do it right. So a couple of things that I do without, I don't say them all the time, and it's important that sometimes I do say them because then you can realize that you could do those things as well. While I was working on my points and getting ready to do them and getting ready for the graph, before I had even graphed it, I thought about what is it going to mean if my y's are multiplied by 3 and my x are multiplied by negative 2. Okay? If my y's are multiplied by 3, my graph is going to get stretched. So I was expecting numbers to be higher than they were originally. When my x gets multiplied by 2, that stretches it horizontally. So I expected my numbers to be wider than they were originally. I also had a negative inside the function with the x. That's going to flip it, because the x values are negative, that's going to flip it over the y. So I knew my original graph looked like this, but I had a sense with the flip and the stretches that my new graph was going to look like that. When I started graphing things, some of my points didn't match up with what my original thought was. So that made me say, I should check my negatives. I should check my mental math just to see if it matches up. And sure enough, I had forgotten the negatives here and I had forgotten a point originally. So it's not a bad thing to have a couple of those checks in place when you do a question. Yeah, it might take a little bit longer initially, but it's going to help you in the long run. Now, this is a good question to do because there's a question in your homework, and we'll just look at it quickly right now. I'm going to look at number 9. So number 9 asks you to graph this. Oh, I'm using my pen that disappears. And they give you this graph off to the side. So there's 2 ways you can go about this question. Okay? You can go about it just like the example we just finished. You can say, I'm going to ignore this graph. I know that this graph is related to y equals x cubed. That's a parent graph that I know that looks like this, and I know points on that graph.
Sorry for the interruption. Ms. Teschner, please contact the office, please. Ms. Teschner, please contact the office.
The difference between this graph and this graph is that I have a -2. So if I'm using this graph, I know that I'm going to have to multiply my x values by -1/2. So it's going to flip and get squished. So what is it going to look like in the end? If I draw it over top, it should look something like this. In the textbook, they said, here's a graph to start with. If we were starting with this graph, how is this equation different from this equation? The only thing that's different is the 2. So if I was using this as my starting graph, the only thing I would notice that was different is just the 2, not the negative. And if it's just the 2 that's different, all I have to do to this graph is multiply x by 1/2, which compresses it horizontally. And my ending graph would look like this. Whichever method you use, notice our final graphs look the same. Prefer to use our regular parent graphs, the y equals x cubed, and notice the differences from that, rather than starting with something halfway along. But this one gave you the starting point halfway along. I think in part B, they give you the regular parent graph of y equals x squared, so that one's a little bit easier. So there's 2 different ways that you could do that question number 9.